given here, the acid plant, but to emphasize the importance of sulfuric acid production in copper smelting, we must remember that it is at least 3 times the amount of copper in tons produced. The other important issue is that we are producing slags, which are circulating in the smelter in various ways, not like in this flow sheet typically, but it is also a large volume byproduct of copper smelting, with a mass of more than 2 times the copper production. So we have large volume byproducts in copper making as well, which must be dealt properly, and which is costly. Not only bringing revenues to the smelter, but requiring money for treating these byproducts properly and storing them in a legal and good way. So we start from very lean material generated in the Earth's crust. We generate mining waste. We generate slag in smelting step, and sulfuric acid in large quantities, and in the end we get 99.99% weight copper cathode, which actually is a end product of metallurgical operations, and includes mine, smelter, and refinery, which do not locate necessarily in the same place in the world. These refineries can be far away from smelters, and mines are where they are. So you don't invent ore body. It is there, and you find it, but you don't invent it. So its location is not up to you. So how we use energy, and how we have used energy in copper making, and this means now the smelting and refining steps after mine site. Mining is actually consuming about 80% of total energy and in copper making, and it is that step we have in terms of sustainability. We have most issues to deal with. So if we look back about 90 years, so the cumulative need or demand of energy in copper making per ton of pure copper was about 70 gigajoules per ton, and its breakdown in the global production chains, including hydro and pyrometallurgy, and also this mining step, were included in that number. So the mining site has this much in the total. So it was about 45% in those years when the copper ores were still rich, containing at least 10 times more copper than average ores today. And that means that the share of this mining step was relatively small, and more energy was consumed in the metallurgical, basically hydrometallurgical, pyrometallurgical operations. 40 years later, situation was better. So 50 years from now, the total energy consumption was probably at the minimum in copper making, and that indicates the development of technologies in mining, concentrating, so beneficiation, and to some degree also in metallurgical side. But after 1970, the ore grades have been decreased much, and also the smelting technologies have been improved drastically. So 10 years ago we had situation where this mining and beneficiation was consuming probably 70% of total energy. Today it's 80 probably, and smelting was only probably 20%, and leaching hydromet operations, they are very lean ores, mostly what are treated in leaching and hydrometallurgical processes. They were having the share of almost the same as pyrometallurgy. So we have here clearly the effect of technology development and depletion of ores visible in these energy consumption figures. So the reason why these in particular smelting operations are relatively energy lean is that sulfides have very large chemical energy content, and in many operations in the smelters, so the furnaces, smelting vessels in the primary phase and also in the converting phase, they are self-sustaining in terms of energy consumption, and this is why copper industry has all the time, already in 1930s, used secondary materials as feed in the smelting, because there is excess energy to be dissipated. So the big difference in energy demand between sulfide smelting and oxide raw material metals like aluminium and iron is in this specific feature that sulfide minerals contain a lot of chemical energy, and the comparison is coming next. So in case of aluminium, we can say that the energy consumption in secondary aluminium smelting is very, very small compared to primary smelting. So if you look at this table, so secondary aluminium smelting is consuming less than 5% of the total energy needed for primary aluminium smelting, and this is a relative number only, because the total processing of aluminium metal from bauxite ore needs huge amount of energy compared to copper smelting. So more than or almost about 2.5 times that energy required for copper making. So it's how much energy is needed in making metal. It's about the primary source of the metal, so the ore, what it is in terms of chemical composition, and how, in thermodynamic sense, how noble the metal is. Aluminium is very, very unknoble compared to copper or even iron. So we need a lot of energy, electricity for electrolytic refining or extraction of aluminium, which takes about 80% of the total energy consumption in aluminium making. So these comparisons may be done from several different starting points. Just comparing total energy use or energy use between various technologies or between primary sources and secondary sources. So you must be careful when comparing and extracting data from the literature, and look the big picture first and then go into details. As I mentioned earlier, there has been a dramatic change in the ore grades over the last 100 years in copper making, but also in other metal production branches. And this picture here shows the trend line, in a way, for copper ores. So 100 years ago, even crushed and ground ore was used as such, as a feed in copper making. But then the ore grades degraded so much that it became impossible in 40s and 50s, and nowadays we don't have such rich ores which could be utilized for copper smelting in the world. So this is challenge for all metallurgists. This is the nature. This is due to our consumption and demand of metals, and that trend will continue. It is sure that all grades will be this average trend line ends at 0.4% of copper in the ore, but we know that there are mines which are operating close to 0.2%, and they must be, to be economic, they must be big mines. They must be mines where the production is huge in order to be feasible. So our technology development, which started somewhere here in 1950s or late 1940s, it has been struggling against this trend of lowering ore grades in copper making. So we have to put more and more effort into grinding and crushing the ore and separating the valuable sulfide minerals from the gangue oxidic stone, which is not containing copper. And since that period of time, so about 70 years ago, there has been strong development in technologies in order to tackle with this problem of lowering ore grades and lowering concentrate grades traded in the concentrate market, and that has meant that we have seen various types of discontinuous changes in the energy use in copper making and all metal making technologies. So we can improve and increase the exploration activities for finding new copper ores. That is happening all the time in the world. But one trend is that when we have lower and lower ore grades, we can tackle that problem by increasing the scale of the operation. So then we lower the total energy use and we start walking on another curve, which is always increasing trend along with decreasing ore grades, and then we will be walking on this thick line until a certain technology improvement is found and and it lowers our energy demand on a new level with the same concentrate grade and the same ore grade, and then our kind of history, or in this case future, will be following this dotted line here. So this is how the technology development has influence, and the economics of scale has influence on the energy demand and basically of metals. And basically metals have a cost which is very closely related to the total energy demand of the processing chain. It is reflecting that simple relation. So more lean ores are more expensive to treat, and thus the metal price must be higher to allow use of such low grade materials and ores and concentrates. So it is in general and in the big picture. One big issue in all metals production, particularly today, is the environmental emission generated by a particular metal. That emission which was most important some 50 years ago was sulfur dioxide. That problem or that issue has been solved today, and already in 70s. I will discuss that a bit later, but today we are facing the global warming due to CO2 emissions, but there are also emissions to soil, water, in addition to these gaseous emissions to air. And in order to treat these emissions, we must spend money. So it's costly, and we need more advanced smelters. We need more advanced treatment methods. And what we also need very much, because this is not or has not been very much voluntary action by the mining and smelting companies. We need international rules and actions requiring responsible behavior in smelting and refining of all metals. And this may be, in big countries, this may be a national legislation, but it may be also international, because in the best case, because these polluting substances, they don't typically they don't be localized. So like emissions in air, they are global. we see sulfur dioxide emissions coming from certain smelters in Asia and South America. We see them in Europe. So it's clear that we need to treat such issues globally, and also water emissions, sometimes also soil emissions, maybe spread out of the country who is actually causing those emissions. So in Europe, on a European level, such rules which are followed by all European Union member states are described in the Industrial Emissions Directive, which is the legislation which later on it is first decided by the European Union, and then it is implemented on local national levels in each country. And this work has been continuing already in Europe already more than 20 years. And we have here documents defining on each branch of metal making, but also other industrial activities, the best available techniques which should and must be used by the member states when this legislation is activated. So these best available technologies are those technologies which are allowed to use in EU, and they are rather detailed documents. The second round of updating these best available technologies or techniques were accepted probably some 5 years ago or something like that. So it's ongoing work where technologies are evaluated based on water, soil, and air pollution and use of energy. And those actions require, and they mean to each producer higher cost of production compared to such companies which are not following these rules. So the responsible behavior in terms of sustainability includes also this global and local emission control to such degree that the soil, water, and air is not polluted locally or internationally. So this best available technology reference document is today called Prof, and it was really updated some years ago. And in copper making we have well-known technologies which are included in these Prof documents. In copper nickel making, we have flash melting and flash converting, and this DON, nickel, direct nickel smelting technology, which then are the best in these technological areas available for the producers to apply. So it means that there are also issues concerned, which are other dimension, which have other dimensions than these pollution issues. So the noise, prevention of accident, and restoration of the site when the smelter or mine is closed. So these are important issues in the future operations. Today we are very much talking about the CO2 and other greenhouse gas emissions, and this is a big thing, big issue for those metal makers who have oxidic ore as the raw material, and the biggest in volume of this kind is iron and steel made out of crude hot metal or big iron, and it has today about 9% of global CO2 emissions, and there's a very strong driving force for replacing the use of carbon in the iron making process chain. So then the options coming after using coke or carbon in general is to rely on hydrogen or biocarbon, and then we may have also other bio-based reductants like biomethane. So steel industry today is putting a lot of effort for producing in the future all metallic iron without using carbon. So one attempt here in Europe is the Swedish hybrid concept, which is piloted at the present time in Sweden, and it is based on hydrogen reduction of iron ore pellets, which are made on the mine site, and then secondary metallurgy operations after that smelting step, which is believed to be carried out. It's not smelting, it's melting step, believed to be carried out by electric arc furnaces, which can also digest a lot of scrap. So secondary as a secondary iron source. This is possible in countries where green hydrogen, so hydrogen made out of typically water, is available, and we will see how the applications develop in the future in geographical areas where only wind or solar energy is available. So the present concept of hybrid cannot be expanded into areas of other metals in practice. So we can do that in certain limited cases for ferronickel production, but not in ferrochromium production, ferromanganese production, silicomanganese production, silicon production at all, because hydrogen is, or actually water is a too weak compound to allow reduction of like ferrochromium and releasing iron and chromium from that mineral. So it's thermodynamically impossible. So this is only for iron making, and the steel making then is carried out by electric furnaces and secondary metallurgy operations before casting of ingots and bars and blooms and so on. So this is a big thing for the world, and there is another big issue, almost having the same amount of percentage or fraction of CO2 emissions, which must be handled probably within 10, 20, 30 years. So that is a cement making, which is producing about 6% of global CO2 emissions, and these two are major polluters of our current civilization. Okay, so as I said about these Profs, they are a series of reference documents covering industrial activities, all industrial activities, not only metallurgical industrial activities. So they are descriptions for technologies to be used and the operation conditions, emission rates they are generating. So in Europe, in European Union, member states are required to take these documents into account when determining what kind of, or allowing permissions for the companies to build in our field smelters and refineries. So it must be according to these directives. But let's go into copper production in more detail, and its technology development and how that has been reflected into this energy consumption and emission issues in a on a global scale. So as you may know, so we have had, not having any more, but we have had several options for making the concentrate smelting into matte. And this is the selection of some 40, 50 years ago, or even 70 years ago, when there is flash furnace included. Most of them have been disappearing. So the remaining technologies are either not listed here, or they are these two actually, flash furnace and Mitsubishi furnace. And these electric furnaces don't exist anymore. Reverbs are probably 2 or 3 in the world, and blast furnaces are not here anymore. But we have some other technologies which have been replacing basically this reverb type of smelting. And after making copper matte, we convert the material into blister copper, and then we do the anode refining, or copper refining into anode copper, and then electrolytic refining. This is necessary because most of copper is used for purposes of good heat and electric conductivity, and that means that the metal must be very pure. If we have 1/10% of something in there, so that typically means 100 times more resistance in the cable made out of that kind of copper. So it must be pure, and our microelectronics is needing even more purity than this 499 copper. All right. So how much then we are emitting carbon dioxide when we are making copper, and how that emission, specific emission, has been developed over the years. So we have several, at least few of these big consulting companies which are collecting data, and those data collections are very expensive. So I have used here data which is about a bit more than 10 years old, and some material is from more recent sources. This is data which typically is not available in university libraries. So that is why this is a bit old, but we can see the trends nicely. So the average copper smelting industry in terms of CO2 emissions is somewhere like a bit more than 1 ton CO2 for each ton of copper produced. This is a relatively small amount, even if it is big amount. but if it is small, if we compare with iron making, so blast furnaces typically use coke and produce almost 1,500 tons of CO2 for each ton of hot metal or big iron. And this is the reason why steel industry is developing these very costly new processes based on hydrogen. The scale is also important here. So 1,500 tons of CO2 for each ton of hot metal as such is nothing. But if we remember that our annual production last year of hot metal was more than 1,300 million tons of hot metal. So this is a big number. And if we compare it to the primary copper making, so mine production, annual mine production of copper. So it was last year about 20 million tons. So it's about 60 iron production is about 60 times that of copper production in the world. But what is important in this figure is that we have flash melting technologies which are and have been always emitting less CO2 than these other processes which are producing, how to say, probably 10% more than the average and 20% more than flash melting technologies. And this is coming actually from the use of external energy in the smelting, which is low in the case of flash melting. So trend has been very good. Trend has been always going down, and this trend is strongly affected by the use of technologies which are energy lean, which are producing copper with as small as possible external energy. So no coal, no coke, no oil. That is the way where we see the future. In 1950s, the big issue in copper industry, nickel industry, and also in power industry was the SO2 emissions, which caused so-called acid rain, damaging forests and buildings in cities. And that picture in this upper right corner is, if I remember right, it is from Germany, from probably 1960s, and it was due to SO2 emissions from copper and nickel and lead smelters also zinc smelters included, and power plants fired with coal. So after 1960s, SO2 washing steps were added in big coal-fired power plants all around the world. That was one step further, and the other step was that copper industry gradually turned their processes into flash melting, where the SO2 capture is very good compared with reverbs or blast furnaces or roasters or electric furnaces using mixed calcine feed. And the trend is shown here. So from early 70s onwards, these are the total emissions by copper smelting which have been realized, and this green area is the estimated reduction by flash melting. So if the flash melting technology would not be in use in such a way and such a fraction of total smelter capacities, so we had have this kind of behavior. So in total, this time period of time from early 70s till mid 90s, some probably 30 or 40 copper smelters were erected with flash melting technology, and this makes the difference. So the downward slope is due to shutting down typically reverbs and blast furnaces. Why this technology this technological step is so huge? That is because reverbs, roasters, blast furnaces, and electric furnaces have so lean SO2 streams in their outlet that it is, and it was 50 years ago, impossible to make sulfuric acid out of that gas mixture. And flash melting, which was originally already producing rather rich SO2 off gas, 15-20%. So it was even more favorable from 70s onwards, when oxygen enrichment was adopted in the flash melting technology. So the sulfur recovery to the acid in the sulfide smelting is important issue, and that is how we got rather quickly this kind of use in forests removed, and nowadays in Europe we don't have problems with acid rain anymore. We have not had since 80s any major problems with acid rain in here. So if we look at the average technologies, so all smelters together in copper making, so the sulfur capture or efficiency has been improved from 19. This is only from 1990s. From 1990s in the world, from about 60% to more than 90%, and flash melting technologies have been always above 90% in here. So the sulfur capture of other smelters, for the very reason I mentioned a few seconds ago, was extremely low, and also there were some, and still are, local problems in this sulfur issue, but they are not major worries on a global scale. So what has been a side effect of this increased sulfur capture in copper and nickel making, also in lead smelting, is that the use of pyrite and elemental sulfur in acid making has been decreasing, and this means that the resource efficiency of minerals processing has been increased as well. So when we are running any metal making plant, so as I showed in some early slides, so we need to constantly think about improvements in technology, and that means lower energy consumption, but it also means improvements, higher recoveries of the metals, and how this energy consumption, specific energy consumption, so energy consumption divided by the produced tonnages of copper, how that has been developing in Europe over some 20-30 years, is that we have been seen decrease in the total energy consumption, and this mostly over this period of some 10 years, from 1995 to 2005. This has been due to increased use of scrap, so secondary resources, secondary raw materials in copper making. So we will see how this curve will behave in the future, but this reduction is about 30%, so it is significant. So and this development is seen here as well. So it's in Europe, where total production of copper is about 2 million tons. So we see a constant increase in the scrap in our smelters feeds, and that has a clear impact in the total energy consumption. It may bring additional headache in the processing and in its refining stages, and we will see how this develops when e-scrap, so electronic scrap will be coming into smelters in large quantities, and requirements about the recovery of minority elements in e-scrap will be faced in near future. But as you can see, the some 10 years ago or 8 years ago, the share or fraction of recycled copper in smelter feeds was already over 30%. So it is a very, very good recycling rate. If you remember what I said about the nature of copper in our societies, where only small fraction of copper produced is available for recycling, and due to that delay when copper is in our infrastructure, in grid, in big electric motors, in roofing, in whatever it is used, so it may stay there for 100 years in use. So how is the status? How much we do recycle metals today? So this UN UNEP survey on recycling, it's rather, how to say, it's rather disappointing to read. So we can follow the recycling of metals in several ways. So we can follow how much of the end-of-life metal is collected. So we call it copper smelting, we call it old scrap collection rate. So that is one numerics in the recycling business, and in evaluating how well societies and industries are performing. Then there is a question of how much of the recycled material, metal and copper in this case, is recovered in the recycling process. So the yield of that material. If we collect 10% of total amount, so the question is how much we get out of that 10% into copper cathode. And then this end-of-life recycling rate, which is somewhat odd measure, which is referring to recycling of all forms of a metal. in this case copper. So meaning more or less pure copper, but also alloys which may contain rather small fractions of copper, like brass and inconel and this kind of metallic alloys which are used and produced for certain specific purposes. So this UNEP report has followed and collected at least rough approximations on how various metals are recycled, and those recycling collection rates are amazingly small if we look at the whole periodic table. So we have here, this is statistics from about 12 years ago. We can see that very few metals are recycled, even half of it. So lead is one of them. Niobium for some reason, and some ruthenium, which is probably a special case. But then these normal engineering metals, iron, nickel, cobalt, manganese, their recycling, even it has been done for decades, it is still between 25 and 50%. Aluminium and some precious and platinum group metals. But then there are amazingly large number of metals like copper, zinc, tin, titanium, chromium, which have recycling rates less than 25%, and many of these so-called new technology metals have recycling rates of less than 10%. And amazingly enough, so some of precious metals and platinum group metals, even if they are so expensive as they are, their recycling is practically non-existent, like osmium and let alone these lanthanum, rare earths, so lanthanides, which are very scarce in availability. Some countries have, or geographical areas have defined metals based on their availability, and so has individual countries in Europe, but also European Union. US has a list of critical metals, and those lists are to some degree living all the time, because the needs and demand of metals by metal is changing all the time. Very few people could forecast 20 years ago or 30 years ago, the huge demand of these metals needed in energy storage, and that has been changing the general pattern very quickly in these lists of critical elements. So it's not anything which is cemented in very strongly in the agendas of the countries, but it is a list of elements which are considered to be sensitive in terms of availability in near future. There is, however, one issue I would like to emphasize here to you, which is the kind of invisibility of some of these high-tech metals which are produced in rather small quantities currently. So this concept of critical metals is somewhat political. It is not coming deep from the scientific knowledge and technological knowledge of ores and concentrates. We know today, because recent surveys on these trace elements have shown that it's a question of pricing. Some metals named as critical in certain areas, like antimony in Europe, has so low price that mining and smelting companies do not recover it because it's not economic. So this is one point. So we don't probably need to worry too much about the shortage of tellurium or antimony or even indium and gallium, because they are available in the raw materials used for other purposes, like copper making, nickel making, zinc making. But an other issue apart from this is that there are also, at least in Europe and probably also in US, some reservations about the mining industry. So some parties and opinions are willing to stop mining entirely. So this has serious consequences. We will see that if we don't have primary raw materials, we don't have either the minority components coming along with those minority those primary metals. So if we don't mine lead, we very soon will see that bismuth availability is a problem. And if we don't mine copper, we don't have new selenium, tellurium, or antimony coming into the market at all. So this is as sad it is, but it is the fact, geological fact, that we need mining for the future generations, and we need ore bodies to be found for the future generations in order to keep the level of these small metals and their availability for the societies. as I mentioned already a few slides ago, some very expensive metals have amazingly low recovery and recycling rates in our present technologies, and it is strange because many of those elements are used in specific purposes, and it is strange that their recycling rates are low. It is clear that element like gold, which is mostly used for jewelry, has a high recycling rate, but at the same time, so we have problems with some platinum group metals, and a lot of them are lost in either collection or processing, which may be due to the small concentrations of these elements in our metal making secondary and primary streams. So this is something I have been worrying about over the last couple of years, and it is clear that we don't have suitable processes and technology development taking place in these elements, which are genuinely rare in the Earth's crust. So this is something where metallurgists of the future have a clear and serious place of developing new technologies for the industry. All right, this is my lecture of today, and now there will be a lot of time for questions and comments and whatever you may have in mind. So please.
Thank you, Pekka. It is so nice. Also, you mentioned before you end that in the future it is need metallurgies to recover some rare metal that's until now it is difficult to recover because yield is very low. Is that true? Yes.
Yes, we
And
have
also,
a lot of challenges.
Also rare earths recycling is still very low. I see also like lanthanum. That's why when I came here, I start to think maybe the reason of that the yield is very low is because we still not understanding very much about the behavior of these metals during recycling, like in the slag and something like that. The limited data, thermodynamic data, maybe that's the one of the issue. Do you agree?
Yes, it is area where severe and strong development work must be done, but not only in the field of processing. So it is also very much a problem in the collection side of end of life rare earth objects. So they
Hello,
often
Pekka?
are present in. Sorry? You don't hear me?
Okay. Can anyone hear my voice?
Questions, please.
Oh yes, question. There is a question in the text in the chat, Pekka, from Dr. Alex Senaputra. He asking about you explain about smelting. He asked about the top side and bottom blown smelting. He asking about top side and bottom blown smelting. The main difference.
Yeah, it's actually the topic of my next lecture on Monday next week. So
Okay.
yeah, so these top blowing, side blowing, bottom blowing expressions tell how oxygen or air is injected in the so it is how the technology has been developed in order to introduce gas into molten matte or slag, and there's also a question about a good book. So I would recommend this copper extractive metallurgy of copper book, which is probably sixth edition is available nowadays. It may be available in your library, and it's available also as a ebook. It's the first author is Mark Schlesinger. He's professor in US in Missouri Rolla. That's a good book in terms of technology, because it is those technology sections have been written by companies producing or developing those technologies. So extractive metallurgy of copper, edition number 5 or 6. Yeah, Davenport is William Davenport is one author there.
So for Dr. Alex, actually, your question is the material for next week lecture from Pekka. Okay, guys, next question, please raise your hand and I will select the participant. Don't forget to open your camera when you are asking. We have a lot of time here still. There's a Nicholas Tandoko. Yes.
Yes, there is one question in the text, but I would like to have my question from microphone. Pekka, thank you for the very comprehensive lecture about metal production from mine to the recycling. You have mentioned about the critical metal recycling or precious metal recycling, and there are some blind spots. We were also thinking about this issue. So what is the main problem or challenge in your mind that we have such a low recovery rate in EU for those precious metals?
Where I can see probably 2 reasons in there. Having been a couple of tens of years in industry, so I know how industrial companies are struggling with these recycling issues, and often platinum group metals are present in copper refining circuits at very low concentrations. So companies have had big difficulties in analyzing what they have in their liquids and and residues, and this may have been confused those companies, believing that they don't have platinum group metals in copper smelting or copper refining circuits, because platinum group metals typically are present in nickel smelting and nickel refining operations. So this may be one source of problems there, but also I think there are difficulties to optimize these pyrometallurgical and hydrometallurgical operations in terms of recovering effectively copper together with these minor elements. So in many cases, companies are focusing on the main metal, and if the minority component is not recovered well, its economic value is not very large, so it is not taken into account. On the other hand, we have companies which are recycling only these precious metals, and they don't want to have base metals in their circuits, so they may be rather critical and select what kind of feeds they take into their specific processes, and this may be another issue where the recoveries are low in metal making. But as I said, there is a clear space for developing new technologies and developing, among others, new analytics for measuring these very small concentrations in our industrial streams of materials. So it will be in focus within a couple of years that when e-scrap feed into copper smelters will increase, so the values of these minority metals will increase also in industry, and then this issue will be important. So it's very much in the future when we will face new technologies for recovering these elements. The same, to my understanding, is valid. The same problem is valid also in cases of these new technology metals like indium, gallium, partly also tellurium, germanium. They are not very well recovered in secondary copper smelting or primary copper smelting. They are not recovered at all in zinc smelting, and I don't know about the lead refining, but I have my doubts about that. So yeah, this will be a future challenge to all of us.
Okay, thank you for the sharing.
Okay, thank you, Longgong. Nice question. Pekka, we have question from Sugam Sukla. Hi, Prof. Can you comment on aluminium recycling, as aluminium can be recycled infinitesimally small times without losing its properties, yet only up to 50% of it is recycled. You thoughts on that, and what are the challenges faced in secondary aluminum productions? In the text, Pekka,
yeah, this is very good, extremely good question. Aluminium is probably the only metal which is not recycled well because of its fundamental properties. So aluminium alloys, there are huge amount of aluminium alloys. They contain many elements: copper, iron, magnesium, huge number of mixtures of aluminium with other silicon, typically with other metals, and we cannot remove those elements from aluminium. So copper is there, iron, even silicon. Those aluminium alloys cannot be refined into pure aluminium, and that really means, as you suggest here, that it is and it may be a rather small fraction of aluminium which is recycled. Here we have a clear example of what happened in Europe and in Finland some 30 years ago. We had to do a decision whether stay with our beverage bottles in glass and probably in plastic bottles. But then there was a great pressure of using cans for beverages, and the initial design of the beverage can was that there was an iron ring holding the cap and the body of the beverage can, and that actually spoiled the whole aluminium, so that it was not worth of pure aluminium at all, and then the design was changed. So now, since 20 years, 25 years, aluminium beverage cans in Europe have been pure aluminium only. No iron rings, no other metals. So this is something which was caused by the requirement of aluminium recycling. We recycle more than 95% of aluminium, as I said yesterday, beverage cans in Finland, and this is because of the change in the can material, and it is true. I have visited our secondary aluminium smelter, which is about 150 kilometers from here, and part of the aluminium alloy they are casting in their secondary refining circuit is actually going into steel industry for killing, for deoxidation of steel. So it is not used as aluminium alloy as such, but if there is iron dissolved and only little of copper, so it can be used for other purposes as a metallic reductant. So yeah, this is a problem which actually I had last week a presentation about that issue in France in a conference. But really, that's a good question, and you need to think about the design for the recycling.
Yes,
that is the key.
Thank you, Pekka. So I also get new insight from here that sometimes we put alloy in material to increase its property, maybe corrosion or reactivity. But however, when it comes to recycle, we have problem. So that's why the reason now Finland, when they designing the can for the beverage, they put only aluminum because they think about recycle and sustainability. So the reason is because aluminum, if it is in alloy form, it is difficult to recycle to its pure form. Okay, and next question is from Nico.
Okay. Good evening, Mas Imam and Mr. Pekka. It's a pleasure to meet you guys for now. Thank you for the chance given to me, as I want to ask several questions to you, Mr. Pekka, particularly. First, it is mentioned that we can use other elements besides carbon as a reductant based on the Ellingham diagram. We can use hydrogen as an option. In fact, using hydrogen as a reductant is possible, and maybe someone just tested it in the laboratorium scale. But is it possible if we use hydrogen as a reductant in the industrial scale, sir?
Okay, is that your question, Nico? So yes, Pekka.
Yes. You are asking whether we can use hydrogen in the industrial scale.
Yeah, because maybe currently most of the industry using coke or carbon as reductant. Yes.
And if
yes,
and if
sorry.
Oh, okay. Sorry, sir. And if there's one, is there an example about it? Thank you.
Example of using hydrogen in industry. I think
yes.
Petrochemistry is a good example. They are using hydrogen in large quantities in their processes, even under high pressure, and also many heat treating protective atmospheres are based on hydrogen. So yes, it is available technology we can take from other industries. So it should be a problem at all in metallurgical industry. So I think it is the same type of issue, not problem, but issue, as 50 years ago when pure oxygen was taken into use in flash melting and other copper smelting technologies. So pure oxygen is very dangerous if you used in the wrong way. And there are lots of examples when the use of pure oxygen in smelters have been causing explosions and even
Pekka,
losses.
sorry, you mean pure hydrogen, Pekka?
Pure oxygen.
Okay.
Where we are using pure oxygen in steel industry, in copper making, in nickel making. So that was considered dangerous some 50 years ago. And I think that use of hydrogen by metallurgists, it is considered as dangerous, but actually there are technologies available how to use it in a safe way.
Okay. Yeah. So yeah, currently even flash melting, Pekka, use almost pure oxygen, right? So maybe currently hydrogen is considered is dangerous, but maybe in the future it will be used in a safety manners with appropriate technology. That's the answer from Pekka, I think.
Exactly.
And
Exactly.
And basically, although we don't use pure hydrogen, there is a technology in metallurgy. It's called HYL. It is used a mixture of hydrogen and carbon monoxide as reductant. All Krakatau still it used that kind of reductant, Nico. But now it's joined with POSCO. POSCO is using blast furnace. They don't use a hydrogen mixture with carbon monoxide anymore. Anyway, so there's kind of technology because the ease of it's from methane. The hydrogen is from methane. Methane is expensive, and again, it's back to economical factor also. And it is not pure hydrogen. It is mixture of hydrogen and carbon monoxide fit to reduce the iron pellet, oxide pellet.
Imam Pekka,
Yes.
actually, I'm very interested with the previous question. Hydrogen has been used in some companies. Do you have any idea about the production of hydrogen? So how did they produce, or how do they produce such a high quality of hydrogen? Yes.
Yeah, using cracking method, Longgong. In my country, the POSCO, the Krakatau still, they cracking methane. They meet methane with water, with water vapor in reformer reactor, and it produce hydrogen and carbon monoxide. I think is that true, Pekka?
Yes, this is the way how this cracking of methane is carried out and has been carried out in decades, but it is not green hydrogen. So what we now talk about in hydrogen economy is that we use green hydrogen,
Water,
which is not actually coming from methane. It is coming from water electrolysis. And electricity for that water electrolysis is coming from solar energy or wind energy or
yes,
hydro
hydropower, yeah.
power plant. Yeah. So when for example, Swedish and Finnish steel company SSAB is piloting this hybrid process where they use green hydrogen. So that hydrogen is made by electrolysis using hydroelectric power. And those electrolytic cells with electrolysis cells, they are today available on a kind of the technology is there, so you can buy such electrolyzers from the shelf. So Longgong, you could look at some literature where this German copper producer Aurubis has published their future concepts of hydrogen economy in copper making, and they plan to use this kind of green hydrogen in anode furnaces and also in other purposes where reductive atmospheres are needed, and that is based on wind energy, to my understanding.
Okay, so very valuable information. I was always thinking about how can we get such a large amount of hydrogen to be the fuel and reductant.
Yeah. And it's really in the future you can't use fossil methane if you claim that you are green. So you have to use some renewable energy source.
Okay, Pekka, we still have a lot of questions here. Okay, next, Nabil.
Mr. Dekmam, thank you for the opportunity. I actually have the question in the same topic as previous question. One of the minus benefit about the renewable energy or green hydrogen is the price for the developing country is still expensive. Do you have any other idea or option, especially for Indonesia, which is developing country? And also to be mentioned, Indonesia has a tons of coal. So I think there is no need to use hydrogen as soon as possible for Indonesia. Or what do you think, Prof. Pekka? Thank you.
We have very few options. We have very few options there. So you have a lot of sunlight. So PV, so photo electron cells are used in large quantities in even in Central Europe, and I would guess that the effectivity of these PV cells are extremely good in Indonesia. You are almost on the equator, and the sun is shining directly from above. So wind energy is also, that is what Finland is building at this moment very much. I think we will have 2,500 megawatts of wind energy becoming on stream this year. But PV electricity is probably the safer solution for Indonesia. I would guess when wave energy is someday available, that would be also possible there, but it's not yet. So wind or solar.
Yeah.
Then you could also think about. Sorry, Imam.
Yeah, sorry, Pekka, sorry.
Yeah.
Yes.
Okay. So you may have some well, this is probably marginal source of energy, but you may have some agricultural byproducts which are producing biomass. You are producing a lot of palm oil, some residues in there. They may be combustible or whatever to electricity, and we are using a lot of biomass in Finland for producing electricity. So it is coming from the wood residues and all kinds of wood residues. So there are green forms of energy, but it depends on the local conditions very much.
Okay. Thank you, Pekka. By the way, I also have one student in Indonesia doing research on the cells, on the photovoltaic things to take the energy from the sun. And we have one more question. Sorry, guys. Last one is from. It's okay, Pekka. We have two questions actually here, very long. One is from Daniel. Maybe you can read, Pekka. It's okay if we finish at 10 past 12.
Yeah, no problem.
Yeah. From Daniel and then from Delvin.
Daniel. Okay.
Yeah.
Nickel being recycled is yes. Actually, this is a kind of battle between two industries. So if I understand you right here, you say that if the battery industry needs very much nickel, so it will not be available in stainless steel industry. Yes, this is true, and that is why, like in my yesterday's lecture, I showed you that there are lots of these nickel-free or low nickel stainless steels which are developed just for replacing these normal 18-8 or whatever these high nickel, high chromium alloys are. So adding manganese, which brings solubility for nitrogen, and that generates strength and stainless properties and so on. So at the present time, I understand that nickel cannot be replaced in batteries. So if that is the case, which will be changed within 10 years or something, so we use all our nickel in batteries, and then there's no nickel for our stainless steel, and that will be limited. The use and distribution will be limited by the availability of nickel in general. Yes.
Pekka, I think the last question is a comment about the hydrogen technology, because when we electrolysis the water to produce hydrogen, it needs energy, and energy is maybe very expensive. And the Delphine comment, I feel like even if we move to hydrogen to produce metal, it will still cause a lot of carbon footprints. How do you think with that? That's why Pekka suggests we use hydropower to electrolysis the water, so it's zero carbon. And also from solar panel. Although to produce silicon, it use maybe pyrometallurgy, I don't know, but still maybe currently is still expensive, Pekka.
Yeah, you're right. You're right.
Yeah. Yes.
But yeah. Yes, it is. You are right. In a sense, you are right. If you make a solar cell, you make pure silicon. As long as we don't have any organic solar cells, or what I was listening last week in France. So there are some perovskite type of structures which are inorganic. They are reaching efficiencies which are close to silicon. So as far as long as we have these silicon-based solar cells, yeah, they will have a footprint, but major as I said, part of carbon dioxide emissions anyway comes from that kind of industries where hydrogen is the solution, and then from cement making where you can't avoid using limestone which contains carbon dioxide. Yeah, so we need to find solutions for the use of limestone in cement making. But yeah, if we build a windmill, we need a lot of steel, we need a lot of glass fiber for making a tower and these propels, wings for capturing the air speed. So I don't know when, after how many years, a windmill will be carbon neutral. So in which stage of its life it will be producing less carbon dioxide that is needed for producing the mill itself. So yeah, these are serious questions, and hopefully the science and technologies are developing in such a rate that we don't need any more silicon. We don't need any more silicon wafers, but we use, for example, thin film solar cells, which are, when silicon wafer is 1 millimeter thick. So this kind of thin film solar cells can be 10 micrometers in thickness. So yeah, so we need a lot of technological and scientific innovations for reaching this target. It's not only that we are, how to say, we are ready to make things like we did yesterday. We need to learn more. We need to develop our things further and so on. But I'm completely in agreement what you say in here, Devin.
Okay, kiitos Pekka. It is 10:12. Still have question, but I'm sorry guys. Time is over. Pekka need to take a rest. It's already 2 hours, and other students maybe do some other things. And here also coming Dr. Taufik Hidayat. Also, Dr. Longgong is here also. By the way, Pekka, I don't know if still here or still Dr. Taufik Hidayat. Yes, still. Okay.
Hello, Pekka. Yeah, thank you for the nice talk.
Yes.
Just wondering who that K is. So it may be even somebody from Australia.
Yes, Taufik Hidayat is here. He will become Min opponent soon.
Yep. All right.
Okay, everyone, nice to meet you. And for you who asked about the materials, so don't worry, we will give you login to ITB system as soon as possible. We're still arranging everything, so don't worry, everything will be posted in the system. You can download the material, the link of the video from the lecture. And see you tomorrow with me. Bye-bye.
Bye-bye.
Bye-bye, Pekka.
Bye-bye.
Bye.